Hi everyone, thanks for tuning into ACM Cyber's first ever virtual workshop. I'm Kimberly, one of the cyber officers. If you've been to our past workshops before, you'll notice that we are doing things a bit differently. Instead of having presentation lecture style, we are going to give you a written walkthrough for you to read through at your own pace. In this video, we will be demoing some simple problems. Then, in our office hours, which we will announce per week, we would love to answer any questions that you message us in our Discord channel. Links to the written walkthrough as well as our Discord channel will be in the description. This workshop is designed to be beginner friendly. That means if you haven't taken CS33 yet or you're currently in CS33, the written walkthrough should go over some of the fundamental information of reverse engineering and the basics of assembly. This will help you practice for CS33's bomb lab without the consequences of exploding your bomb and affecting your grade. If you have no idea what I just meant by exploding your bomb, don't worry. Professor Reinman should soon cover this material in class, which will mean you have a head start in digesting this material earlier. If you have already taken CS33, that's also great. This is an awesome opportunity for you to practice some reverse engineering and brush up on your assembly skills. With all that being said, before watching this video, please read through the written walkthrough first, and don't forget that you can ask questions on our Discord channel. Okay, so let's get started. Let's begin, as all programmers do, with a simple Hello World program. In this example, I will be writing in C, but you can use any programming language that you're comfortable with, including C, C++, or any other language. Unless you already have GDB installed on your local machine, I would highly recommend using UCLA's Linux servers when testing your programs and using GDB. And just to emphasize that this is a beginner-friendly workshop, so we will only be covering the equivalent of Bomb Lab Phase 1 through 3. So tune in next week to find out more about GDB and practice for Bomb Lab Phases 4 through 6. So before we begin, I already connected to UCLA's VPN over here, and so I should be able to SSH into my Linux account. So before I start, let me increase the size so that it would be easier to see. Okay, so I'm gonna SSH into my account. All right, so the first thing I'm gonna do when demoing this, because I don't wanna just put it anywhere, as you can see, I have a lot of folders. So I'm just gonna make a new directory with the command mkdir, and then cyber demo. And then I'm gonna change directory, so CD into that folder, into that directory. And now I am in that folder. To write my Hello World program in C, I will be using Vim, a text editor, but feel free to use anything that you're comfortable with, including Emacs. So the first thing I'm gonna do is do vim hello world.c and then write out my simple hello world function. So the first thing I need to do is include and then begin my main function. Please don't hate me for my curly braces. And then I'm just gonna do a simple return. Seems easy enough. I'm gonna save really quick by pressing escape and then :WQ. And now I can run it. So really quick, feel free to do this on your local machine. For example, using Sublime, using Visual Studio Code, using Xcode, and then importing it using SCP or whatever file transfer program that you're familiar with from CS31 and 32. So what I'm gonna do now is I'm going to compile this program. So what I will do is do gcc-o hello, and that's the name of my executable, and then I'll call the function, so hello world, and continue. So it's good, it has compiled without any issues. And then what I want to do next is get the assembly of this program. So I will be doing object dump -d and then the name of your executable, which in this case is hello. So really quick, going back to the gcc-o, if you read through the written walkthrough, it will help explain that as well. And you can also be using the -G flag if you want to use any symbolic debugging information, if you want to include any symbolic debugging information. So if I press enter, object dump -D, so I spelled it wrong, then you'll see all this assembly. And if you compare it to our original program of around 5-6 lines, as opposed to all this assembly, you'll see why assembly and reverse engineering is so tedious. First thing that we want to do is go find that main function, because we know that that's the only function in our program. So really quick, I just pulled up the source code file on the left, and then the assembly will be on the right. That way you can compare between the two very easily. So we found the main function, and in it we see push register RBP, and that's the first instruction over here, if you can see my mouse. So looking at these first two instructions, we see that we are moving RSP, register RSP, into register RBP. And so you remember that register RSP is the stack pointer and register RBP is the stack base pointer. So what these two instructions are essentially doing is that it's keeping track of where the next instruction will be executed, and that will be where the stack pointer is. Moving to the next instruction, instruction number 400506, we see that we're moving this hex into register EDI. And if you don't remember what EDI is, don't worry. You can go back and check in the walkthrough where and what EDI is. So register EDI is the lower 32 bits of register RDI. And RDI is the register where data is copied into. So we now know that there must be some kind of hexadecimal being moved into this register EDI. Right now, we don't know what this hex represents. But if we use GDB, we can very easily verify what is being moved into this register. So we can go through that GDB really quick, but let's first continue through all the rest of the assembly. So we see in instruction 40050B that we're moving 0 into register EAX. And register EAX is also the lower 32 bits of register RAX, which is the return register. So essentially what we're doing is putting 0, remember this is the source, into register EAX, which is the return register. And that's the same as this line over here in our C source code where it says return 0. We see after this instruction is executed, it will be printing some kind of function, which makes sense because in our C source code, we see that there's a printf. The next instruction is already explained. We're moving 0 into the return register, and then we're popping RBP. What popping RBP is that it will be popping the stack base pointer so that we can return. And what will be returned is in the return register, which is register EAX. Okay, so let's go through this GDB really quick. So really quickly, I'm gonna clear my screen to make it easier. So to first launch GDB, what you wanna do is just do GDB and then the name of our executable. If you forget, you can do ls to list your directory contents. We see that hello is our executable. So we will be doing GDB hello. And now we're in GDB. So in order to run it, we just press R and then we can start running. And as you can see over here, it prints hello world, and that works as intended. We haven't set any breakpoints, but in the next workshop next week, we will be going over how to set breakpoints so that you don't accidentally do something that you weren't intending to. Okay, so what I've done is I pulled up the assembly on the left, and then so that way when we're running our GDB, we can have the side-by-side comparison. So what we originally wanted to examine using GDB is what is this hex symbol representing? So in the next workshop, like I mentioned earlier, we will be going over how to set breakpoints, but for the time being, we can also use GDB to examine what's inside this hex, or what does this hex even mean? So if we do examine, which is a shorthand would be X dash, and let's just, to be conservative, we can do 20 bytes, which would be 20 XB. And then we have to put in the hexadecimal, which we see right over here, 0x4005A4. And then we see all this beautiful hex. So something that I've done in the write-up is I went through the ASCII and the hex table and converted each one. And if you don't trust me, you can go over and look through each individual hex, and you will see that 0x48 is H, capital H, 65 is E, 6C is L, L, O, space, W, capital W, lowercase o, R, L, and then 0x64 is D. 0x00 is null, which is the equivalent of saying this line is over. So after this, we don't really need to go through each one, but if you look at the conversion table, you will see that it doesn't really matter. All right, so now you've successfully interpreted one Hello World program in C, and you're able to disassemble it and look through the assembly language and find what exactly is going on. If you are following along with this demo, don't be alarmed if your addresses don't exactly match up. What's important here is that you understand the general logic of each instruction and know what they're doing in the overall source code. Okay, now let's move on to the next demo. In this demo, we will be doing a simple if-else statement. This time, I will be using C++ so you can follow along. I will be using my text editor once again, so I'll do vim, and then let's call it if-else.cpp, and then press enter, and then we can start typing our program. So include the IO stream, using namespace std, okay, let's define a variable. Let's call it start. And then to tell the user to input some information, let's do cout, enter an integer, end line, and then we're gonna cin that variable. And then let's do a simple if-else statement. So let's say if that start variable is greater than 2, we'll return that start. Otherwise, we will return 0. And let's just do a return 0 just in case. Okay, let's save that. So let's compile this and get the object dump of it. So notice how it's slightly different than C. Instead of GCC, we will be doing G++, -o, and then let's call our executable if-else, and then we'll call the CPP function, or CPP source file. Press enter, and you see that it compiles without any errors. The next thing we'll do is get the object dump. So obj dump-d, and then we'll call the name of the executable, which is if-else. Press enter, and we'll see we'll have a bunch of assembly. So let's jump to the main function right over here. And we see that it's pretty long. For an if-else source code, here, I can pull it up on the right. All right, so what I've done is I pulled up the source code on the right so you can compare it to the assembly on the left. So let's simplify our if-else CPP, and let's get rid of the C and cout, and just temporarily so we can understand the assembly first. So let me comment it out. And then let's define start equals a random number, let's say 10. And then let's save this, and we can also get rid of this return. So after we save the file, we need to recompile it just to see if everything is good. So once again, it's G++-O, and then let's call the executable if-else, and then call the source file .cpp. So now we can do the object dump of this. So object dump-d, and then the name of the executable. And if you press enter, you will see this again. And this time, our main is a lot simpler. So this is just for the sake of understanding how if-else statements work, so I simplified it. So let's go instruction by instruction like what we did with the Hello World program, but this time you can go a little bit faster because you're now more familiar with it. So let's look at the first two instructions of the main. It says push RBP, and then we're moving RSP into RBP. And so remember from the last demo that register RSP is the stack pointer and register RBP is the stack base pointer. So the next instruction to be executed will be the stack pointer. And also notice that the first two instructions are identical to the first two instructions in the prior example in the Hello World C program. And you will begin to notice a pattern the more assembly problems you practice, which is why it's so important. So let's move on to the next instruction 400616. And we're moving 0xa, which is the hexadecimal representation of the integer 10. And we're moving that integer 10 into this register with the offset of -0x4. And what this does is that it ensures that when the base pointer is called, it can return to the function again, which is why we need to add this offset. The next two instructions is CMPL and JLE. What CMPL is the comparison operation, and JLE is the jump if less or equal operation. So we see over here that there's a comparison of 2 to our original number of A, because remember we moved this A, which is representing 10, into this register over here. So we're comparing if 2 is less than or equal to 10. And if it is, then we will be jumping to 400628. And if we see over here, 400628 is moving 0 into the register EAX. And if you recall, EAX is the return register. After that, we will be popping the RBP, and the RBP is the stack base pointer, and then we will be returning. So that makes sense, right? So we are only jumping if 2 is less than or equal to 10, which makes sense because over here I can add a comment. So let's say that it didn't evaluate to true. This comparison operator did not evaluate to true, and the instruction was not less or equal to, which means that it was greater than. So 2 was greater than whatever variable is in here. Then we will be moving past this jump instruction and going to the move. What this move does is that we are moving that original variable, so this is representing our start variable, into the return register. And then we will be jumping to 40062D, and if we see 40062D is popping the RBP, and then we're returning. So what we are returning is what's in the return register, EAX, and we just moved our start variable over here into the EAX. So now you have executed this entire program using assembly. All these instructions will also be written in the written walkthrough, so if you didn't catch something, you can always go back and reread it too. Alright, so let's go to our last and final demo. We're going to be demoing what a for loop will look like in assembly. So I will still be writing in C++, so let's get started. Let's do vim, let's call the program forloop.cpp, and then as per usual, we need to include IOStream. Using namespace std, and then we'll start on our main function. Let's use the same variable again and call it start, so int start, and let's initialize it to 0. So let's write out our for loop. For int I, and then let's initialize that to 0. If I is less than, let's say 10, then we will keep increasing I. And then inside our for loop, let's just increase start by 1 each time this loop is run through. And at the very end, we shall return the variable start. All right, so let's save that. And then on my left, I'm going to try to compile it. So G++, let's call the executable for loop. And then let's call the CPP file. Press enter. We see that it compiles with no problem, which is awesome. Let me pull up the source code on the right, so that way we have an easy comparison. And on the left, let me get the object dump again. So obj_dump-d, and then for loop, the name of our executable. Press enter. We see all this assembly, but remember, we only have a main function on our original source code, so that's what's important. So let's go find it. And we see it over here. So we see that the first two instructions, push RBP and move RSP into RBP, is the same. So I will just be saying the same thing again, so hopefully it can get into your brain. RSP is the stack pointer and RBP is the stack base pointer. So that way we know where the next instruction will be executed. All right, so let's move on to the next instruction. Looking at instruction 400616, we see that we are moving 0 into this register. What this register is that it's representing our start variable, because if you look at our original source code file, we see that we're given an int start. So that's what this register is representing. The next instruction with a different offset of 0x8, which is the integer value of 8, it must be storing another variable, and in this case, because we do have the source code side by side, we realize that that is actually the int I variable. So from these two instructions, 400624 to 400628, we realize that 9 is being compared to I, and if it is greater than, then it will be jumping to the instruction 400634. And so let's do that. Let's follow along. 400634 is moving 0x4 RBP, which is what we defined earlier as a start variable, into the return register, which makes sense because we see over here in our original source code file that we're returning start. And then afterwards, it's the same. We're popping RBP and then returning. So we're going to be returning start. So that all makes sense, that if 9 is greater than I, then we will be returning. So we are getting out of this loop. Let's say that these two instructions did not evaluate to true, so it wasn't able to jump to instruction 400634. What happens is that it goes to the next instruction, which is adding 1. These two instructions, instruction 40062A and instruction 40062E, is adding first 1 to the start variable, which makes sense. We see it over here with the start plus plus, and then adding 1 to 0x8 RBP, and that's our I iterator, and after each loop iteration, we do I plus plus. The next instruction is jump to 400624, and we see that it goes back up to this comparison once again, and it will keep checking if I is greater than 9. If it is, then it will be exiting this loop and returning. So now we have seen that this is how a loop will be executed in assembly. It's certainly more complicated than what we see in C++, but this will help you understand how the assembly works. Please also note that during this demo, I had the source file and the assembly side by side to make things simpler. However, in CS33, you will just be given the executable, so it's up to you to figure out what the assembly is really doing without seeing the source code. If you have any questions, feel free to stop by our office hours or message us in our Discord, and me or one of the other officers will try to answer as soon as possible. Tune in next week for more advanced assembly and learn how to really use GDB and get some practice on the harder bomb lab phases 4 through 6. Thank you.